So my name is Ross Burns. I'm going to be giving a lecture today about masers at this DARA training. So this is actually my third DARA training. The first time, though, that we're doing things, recorded or remotely. It's really unfortunate that I couldn't be there to meet everybody and see how everyone's doing and things. But it's just how the situation is. So I really hope you're having a good time and learning lots of things at the I think everyone's at the Ghana station, right, in Kuntunze. But in any case, I hope you're really enjoying learning lots of stuff, and you're in very safe hands. I know that Melvin and Provin and Benedicta and everyone's hopefully with you, so you'll be fine. So I'm going to be talking about masers, and since you're studying now radio astronomy, you're going to be hearing a lot about masers in a lot of different contexts. So you'll hear about masers in the context of maser clocks. That's not what we're going to be talking about today. We're talking about astrophysical masers, so the masers that are up in space, the ones that we observe. And the reason why they're kind of important is in terms of radio astronomy, in terms of the kind of objects that you can look at in the sky, they are some of the brightest things that you can see. So I wonder if I can make that not happen. Yeah, they're some of the brightest things you can see, so they're used a lot for calibration, telescope pointing, stuff like this. So if you're doing radio astronomy, masers are unavoidable. And I would say masers are the best, but I'm slightly biased. Anyway, okay, so let's start. So what is a maser? And I should mention that in this lecture there's going to be maybe 0 equations. I don't remember, maybe like 1, but no real kind of math. This is going to be mostly conceptual. So I want you to really kind of get ideas and an understanding and a feeling for these things. So I'm sorry if some of this seems at the beginning a little bit kind of simple, but it will gradually kind of build, and hopefully this kind of logical flow will be beneficial to most people. So what is a maser? Again, we're talking about astrophysical masers, so the question really should be, what is an astrophysical maser? And it's essentially a cloud of gas, only this gas has a special property that it has population inversion. So I want to discuss what is population inversion on the next slide. But to give some kind of general knowledge of masers, so you think about some cloud of gas up in space somewhere in some kind of situation. We'll talk about what kind of situations later, but it's a cloud of gas, and that cloud is made up of molecules. And so let's say you have a water vapor cloud. It's a cloud that contains lots of water vapor, and this makes sense. And for some reason, some of these clouds can produce something called maser emission. And the kinds of molecules, clouds of these molecules that can form masers, there's this list here, which I stole from Wikipedia. But in the astrophysical context, the masers that you see a lot of they're written here on the bottom left. So it's hydroxyl, methanol, water, and SiO. So these are not the only masers. As you can see, there's quite a big list. But these are probably the most common ones that you are going to encounter, and I'm going to talk a little bit about each later. So these clouds that are the maser gas clouds, are the ones that produce the maser emission. They can be anything from smaller than an AU, astronomical unit, to 100 AU or so. I myself study VLBI, so the masers that we look at are typically around about 1 AU or so. But when you're going to be using the radio telescope, you will be able to see more extended masers on the sky as well. It's nothing too important to think about, but just the important thing is this concept that a maser is a cloud of some particular molecule species, and that cloud, the molecules in that cloud are in population inversion. Okay, so what is population inversion? So first we have to discuss what is not population inversion. So this is a normal thermal distribution of molecules. So if you were to have like some normal cloud, literally like say like a cloud in the sky, and you were to take all the water molecules in that cloud and measure how many of those water molecules are in a low energy state, how many of them are in a medium energy state, and how many of them are in a high energy state. And if you were to count them all up, you'd have what's called a Boltzmann or a thermal distribution, where, much like people, almost everyone's in the low energy state. There's a few that are kind of a little bit excited, and then there's these kind of the ones that are set apart that are extremely excited. So this is the kind of normal case that you will have in any kind of normal cloud, like thermal clouds. So when you look at, like, say, the giant molecular clouds and stuff, typically it's going to be mostly like this. So then population inversion is where, for some reason, you have more molecules in one of the higher energy states rather than one of the lower energy states. So this is why it's called inversion, right? Because you typically expect to have more at the bottom and fewer at the top, like this. And it doesn't really matter, this is a 3-level system, so it doesn't really matter which one has the most, but population inversion is achieved when any one of the kind of higher level energy levels has more molecules than one of the lower ones. So there's various kinds of population inversion you could have. You could have, say, like all of these up at level 2 there instead of level 1. That would still be population inversion. But anyway, yeah, not more at the bottom, but instead inverted to be more at the top. So that's population inversion. So then how do you get population inversion? Bearing in mind, so I want you to remember, just so that we don't forget, these are just, if you count up the different energy levels of molecules in the cloud, right? And a cloud like this. That's all we're doing here, okay? So just remember that this is a physical cloud. So to get population inversion, what we really need to have is at least a 3-level system. So a system where you can have at least 3 energy levels. Energy levels, I'm pretty sure you would have studied this in some other contexts and things, but for example, you can have like rotational energy levels, or what's that one? Torsional energy levels, vibrational energy levels, and then you can have like the ionized energy levels and stuff like this as well. So this is the kind of energy levels we're talking about. So let's say you have this 3 energy level system, and you have some input energy, which is taking molecules from the lower level and pushing them up to the higher level. And I think you probably would have studied in some contexts this idea of the Einstein coefficients. So these are ways of calculating the decay timescales of molecules in energy levels. So every molecular transition will have some Einstein coefficient which predicts like how what's the rate of that transition happening naturally. Okay, so you have your 3 energy level system. You have some input energy, which is taking molecules from the lowest energy up to the highest energy, and this can come from various sources. This energy, it can be radiation energy, so photons coming in. It can be collisional energy, so this is where you have stuff bashing into each other. Stirring some water is adding collisional energy. Putting something in the kettle, guess that's radiative energy, right? Heat transfer. Oh, I don't want to go down that rabbit hole. Anyway, okay. So you have this source of energy pushing molecules up to the top, and then from this level 3, so you can see the energy levels are numbered 1 and 3. I don't know where 2 is, but whatever. So you push things up from level 1 to level 3 with some energy input, and then if that Einstein coefficient for between level 3 and level 2 has a fast decay, then you're going to very quickly pile up a load of molecules in the level 2 position. Then if from level 2 to level 1 is a slow decay, then you're going to end up with this kind of traffic jam where there's things stuck on energy level 2. And this is then you've formed your population inversion. Okay? So now you've got your population inversion. Where does the maser emission come into this? And every time I've come to DARA and I speak to everyone, and it seems that a lot of people there are pretty clued in with stuff like IT and telecommunications and stuff like that. So the idea of a laser is, doesn't really need to be explained. But I think it was, what's the acronym? It's light amplification through stimulated emission of radiation. So you have some system like this. You have the population inversion, and then when a photon comes in, it will stimulate the drop of molecules from level 2 to level 1, and this is going to produce a photon of frequency nu, where you have E equals h nu, and this frequency of light is going to be the same as the photon that stimulated the emission. So for every photon coming in, you then have 2 coming out. Okay? And the kind of important thing to remember is that the 2 photons that come out are of the same frequency than the 1 photon that came in. You have one, and then you stimulate another one of the same frequency. So the original one still continues, and you have a new friend. So what happens is you're amplifying the light through photons, and you're amplifying it at a very, very narrow frequency range. So it's not that you end up with longer wavelength photons and shorter wavelength photons. You just end up with loads of photons at the same frequency that corresponds to this difference in energy levels between energy level 2 and energy level 1. So from basic chemistry and physics that the frequency of this light corresponds to the difference between the 2 energy levels in the transition from which it moves, right? Okay, so I think this is probably explained at a level that's pretty easy to grasp for everyone here now. So now I want to talk about the path length through the maser. So we discussed this population inversion, and we discussed now the maser emission process itself. Now I want you to think about if your maser, the physical maser cloud, is actually very long. So you have a photon that comes in, and it encounters this population inverted gas, and what happens is you have this stimulated emission, the maser emission. So this is kind of, say, here at level 2. So now you have 2 photons going through the gas. But as long as there's still more gas ahead of you, you can do that again. You can repeat this process. So your 2 photons, each of those 2 photons now are going to stimulate the emission from this population inverted gas, and now each of those 2 photons produce each 2 photons. So now you have 4 photons. And then you see where this is going, right? If you have more and more gas, if your maser cloud is very long, you can do this more and more and more times until you end up with a very, very bright output coming out of your maser at the other end. So you have 1 photon coming in at one end, and then bazillions of photons coming out the other end. So I think this might be the only math in the entire presentation, but the amplification goes as the exponential of the path length. So if you double the path length of your maser, then your amplification, so let's say you have 1 photon coming in, 2 photons coming out. If you double the path length of your maser, you then have 1 photon coming in, 4 photons coming out. So e to the power of the path length. Okay, so what happens then is you put your telescope, or you have your telescope receiving these photons, and I mentioned before that the frequency of the additional photons that get produced are the same as the input photon. So this causes you to see maser emission as being a very narrow spike in frequency bands. So I just put in this little kind of example figure on the right here. I'm wondering if you can actually see my cursor. If not, then that's very unfortunate. Let me just check. Sorry for this. Oh, I don't know how you check if you can see the cursor. Well, we're just gonna have to hope that you can then, I'm sorry. Yeah, so this is kind of an example of what maser emission typically looks like. And if the maser is elongated, so this long path length, in a direction that is pointing towards your telescope, then you will see a very bright maser. Okay. Hold up. Hold on. So, if your maser is not quite so long, then the difference being, I mean, you still have the same process, you still have this repeating of stimulated emission, but you just don't have enough length through the gas to provide enough opportunities for this stimulated emission to happen. So yeah, basically if your maser is not so long, then the emission that you see in the end will appear weaker. It doesn't really have much of a handle on things to do with the gas properties. It's just this effect of the maser length in the direction towards the observer. So this is what's known as a beaming effect. And by considering this process, one thing to bear in mind is that let's say you have an elongated maser cloud, and you imagine what it's like to observe it from different directions. So let's take, if you were stood at position 1 here, and this photon is coming in and is going through the maser in a direction that has a lot of path length. So it has a lot of opportunities to stimulate emission, and then each of those 2 photons stimulating another 2, and then to produce this exponential amplification through path length. So somebody observing from perspective 1 is going to observe a lot of photons. Then someone from perspective 2, then, it's still quite long path length through the maser, but it's not as long. So they're not going to see such a bright emission. And then someone from perspective 3, the photons coming through the cloud are coming through in the, say, like the width direction, so there's just not very much path length to amplify the maser. So the important thing to consider then is that this is the same maser cloud, right? But observing it from different angles has the effect of it appearing brighter or weaker. But the cloud is the same. It's I think that's pretty interesting, right? So you have to be pretty careful when you're looking at the brightness of maser emission, because as you can see in this example, the brightness itself doesn't necessarily correspond to how much physical gas is there. It might be that there's not very much physical gas, but it's all pointed towards you. Or there might be a huge reservoir of gas, but it's not very long in the direction towards you. So you have to be careful with masers. So yeah, this is kind of just shown in another example. These 2 maser clouds are the same. So you have the top scenario, bottom scenario. These 2 maser clouds are the same size, but their orientation to the observer is different. And this is going to affect how bright the maser emission is measured from the position of, well, from the perspective of observer 1 and the perspective of observer 2. So you might want to imagine, like, let's say this cloud is rotating, right? It's going to look like it's getting brighter and weaker and brighter and weaker to you over time. But that's something that's actually being studied at the moment in simulations and also possibly in observations. So yeah, despite the 2 masers being the same size, the path length to the observer is different. So observer 1 sees much brighter maser emission than observer 2. Okay, so path length, important. Got it. So I want you to take a little bit of time to basically discuss some things with whoever is nearby, and just to test your understanding, and yeah, just make sure things are kind of making sense in your head, and just to test yourselves basically. So I want you to discuss with someone around you, what is the acronym of laser? How does a laser work? So this is not masers now, this is lasers. What is the energy source of a laser, and what determines its color? Then after you've discussed that, then I want you to think about what are the differences between a laser and a maser. So some ideas here are written in parentheses. You can have like the size, whether it's natural or man-made, what are the wavelengths that you typically get. I'll give you a very big clue there. So what is the M in maser and what is the L in laser? So that's your wavelength right there. But I won't give it away anymore. So I'm hoping one of the assistants is going to pause the video now, and I'm gonna hope that someone unpauses the video when you've finished discussing. So yeah, see you in a second. Okay, so the thing I'd like to discuss next is the pumping conditions. So we already talked about this population inversion, and I hope you remember way back when I mentioned that to have this population inversion, you need to have some source of energy that is lifting the molecules from the lower state up to the third energy level, so that they can fall down onto the second energy level then and produce the population inversion. So I mentioned that the main sources of this energy input things like radiation and collisions. So I want to discuss now a little bit more about these things. So masers, when we talk about making population inversion, we call it a pump. And this is just terminology that's been around for a long time, but you need to pump the maser, you pump the gas to make this maser emitting population inversion scenario. So this is there's been a lot of investigations into what are the conditions in which different molecules produce maser emission. So this is here the case for water masers. These same kind of investigations have been done for SiO masers, OH masers, and methanol masers especially. And there are different kind of physical parameters where the maser will or will not emit. And I want to give some examples here now. And this is one of the most useful parts of masers as observational tools, actually, because they're very sensitive. You'll only get maser emission in a very narrow range of physical conditions. So why that's really great is because if you see the maser in some environment, then you know that those physical conditions are being met. So for example, the methanol maser at 6.7 gigahertz, this is produced in a temperature range of, let's say, around about 100 to 150 Kelvin. So if you can see the 6.7 gigahertz methanol maser, you know that part of that cloud, or that part of that star forming region, or that part of whatever, is in the physical range of, temperature range of about 100, 120 Kelvin, okay? So their sensitivity to the physical conditions is really, really useful for observations. So I'm going to now talk a little bit about the water maser situations. And it's not really important to remember any of these. I want you to just get your head around the concepts of these different scenarios. So, once you understand this plot, which I'm going to explain now, then this idea of using masers as observational diagnostics will make a lot more sense, I think. And I think you'll be quite excited about using them, hopefully. So I'll start, where shall I start? I'll start with the bottom left case. So if you can see my cursor, I don't know if you can, it's this little blue square down here on the bottom left. So the parameter space that we're looking at here, we have on the x-axis we have shock speed, and on the y-axis we have the density. So I mentioned about what is the energy input to make masers. In the case of water masers, this comes from collisions. They also need certain amounts of radiation in the environment, but the main source of energy is collisional energy. So this is why the shock speed, you can think of it as being a proxy for the collisional energy. So the faster the shock is going, which is the x-axis, the more collisional energy there is. And then the density is literally just the number density of molecules in the cloud. So if we start here on the bottom left, so the shock speed is at its lowest here. And you can see on the actual plot itself it says too cold. This means, there's not enough energy. So I added this, the main plot is from a paper from Hollenbach, but I've added these little kind of subplots here. So in the time where the shock speed is too slow, there's just simply not enough energy from collisional energy. There's not enough collisional energy to pump the masers up to the level, higher energy levels, for them to then cascade down and produce the population inversion. So yeah, there's just not enough energy. The collision speed is too slow. That's unfortunate. No masers for you. Okay. Now, if we were to increase the collisional energy, so that's going to take us over this line, the vertical line, at about 15 kilometers a second, and then you start to have situations where you have maser emission. So the square on the top left, the green one, now you have enough shock speed, enough collisional energy to pump the maser emission. You see that, it's not masers everywhere. Below about 10 to the 7 molecules per centimeter cube, there's no masers down here. And this is because there's the molecules, the density of molecules is too low, so they're not bumping into each other quickly enough to pass this energy from molecule to molecule to produce the population inversion. So there's not enough density of molecules for this collisional energy to produce the population inversion. So you need to have at least 10 to the 7 molecules per centimeter cube. Okay. If you then keep increasing the this is written as starved. So I just want to go back to what I was saying a second ago. Yeah, we call this situation when there's not enough molecular density, so number density. We call this the maser cloud is starved. There's not enough molecules basically to produce the population inversion. I think this probably makes sense to you. If not, then please do ask Proven and Benedicta, because I'm pretty sure they'll be able to explain this. Okay, so let's say now we have enough collisional energy, we have enough density, and now we let's go to this population inversion on the right, so the green one on the right. So again, here we have the right physical conditions to produce the maser emission. So we have, as the collisional energy goes up, the necessary number density is a little bit lower. So we can still produce maser emission. Let's say the bottom right part of the J shock H2O maser region, the white stuff here. So we have enough collisional energy to kind of get past the problem of there not being enough number density. So this is why this the J shocks region kind of curves over. The kind of part I want to explain last then is this quenched region up here on the top right. So what happens is, let's say you have a high shock speed, so you have a lot of collisional energy, but you also have a very high number density. And what happens is the number density and the energy density is so high that all of the molecules pass their energy between each other very efficiently, and then this actually produces the original state of matter, which is the thermal distribution. So what we call this is being is written here as quenched, but another way we call it is thermalized. So you thermalize the molecular distribution or the energy distribution of molecules in the gas by the collisions passing the energy very efficiently from molecule to molecule, and it goes into this state. When you're in the quenched or thermalized state, you don't have maser emission, so there's no maser emission there. So I think you can kind of understand these different scenarios. You need to have enough masers with enough energy from, in this case, collisions, but without there being, too much energy or too many molecules. So yeah, this is why the masers are going to appear in a very narrow range of physical conditions, and these have been studied, and thanks to them being studied and figured out, we can then use them as molecular observational tools. Let me go next slide. Oh man, not enough collision. We should have gone through that. Okay, so we talked about the path length through the maser. So the longer the maser, the brighter it's going to look. We talked about the pumping conditions, which is what we just discussed a second ago. Now I want to mention the seed photons. This is the last of three topics to discuss, but I mentioned this last because it's the easiest one. So let's say you have these same cloud, same maser cloud, scenario 1, scenario 2. In scenario 1, 1 photon comes in, 4 photons come out. In scenario 2, 2 photons come in, 8 photons come out. So the more seed photons, so the number of photons coming into the maser, the more photons you have coming out. So I think this one doesn't really need explaining any more than that. Okay, so we've talked now about 3 different things that determine the brightness of an observed maser. So this is the path length, how long it is to the line of sight of the observer, the pumping conditions, so collisional energy, number density, stuff like that, and the seed photons, how many photons are coming in. So if you wanted to summarize everything we've talked about so far into one plot, then it would be this. So in gray we have the 3 different ways of increasing or decreasing maser brightness. And one thing I should mention that hasn't really been mentioned yet is what is the source of the initial seed photon? Well, this can be a star, nearby jet, or the CMB, the cosmic microwave background. What you have to consider is that, so for any particular maser transition, so let's say we're talking about the 6.7 gigahertz methanol maser, that seed input photon needs to be at 6.7 gigahertz, right? Because you need to have the stimulated emission, you have to have the input photon having the same energy, based on its frequency, as the difference between the two energy levels. So radio frequency photons are the seed photons for radio frequency masers. That's what I'm trying to say there. So yeah, if you wanted to change the maser brightness, ways of doing that would be to increase the path length or decrease the path length, enhance or mess up the pumping conditions, and increase or decrease the seed photons. I want you to discuss again, if you don't mind, with your colleagues to check your understanding on these things. So just ask each other a little bit about these 3 different processes, and just check each other that your understanding is about right. So I'd like to ask Provin or Benedicta to pause the video at the moment, and then unpause when you're done with discussing. Okay, so what I want to discuss now is what exactly masers trace. So the masers that we've been discussing up until now have been these kind of hypothetical clouds in our minds. We've kind of alluded to the fact that they're in space, but where are they in space? So I want to talk about what do masers trace. The most typical kind of contexts that you hear masers discussed in regarding astrophysical masers is going to be protostars, so star-forming regions, and evolved stars. There's also masers in comets, planetary atmospheres, supernova, and extragalactic disks. So those are called the megamasers, the ones in the disks of distant galaxies. And I'm not going to talk about any of these here. They are very interesting. I've studied a little bit about some of them, but myself, I'm very much interested in the protostars, and I work a little bit on the evolved stars. But these are kind of going to dominate the field of maser observations. So if you're thinking of getting into masers, you're probably going to be moving into one of these two. So taking these two scenarios and kind of making schematics out of them, we talked about the different maser species having different initial energy sources to produce this pump. In the case of water masers, this is from molecular collisions. So what that means is you're going to find water masers where there's collisions. Not too many collisions because you're going to thermalize the maser, but where there's collisions. So in jets, in shocks, in like expanding clouds and things like this. Then the methanol masers, this is like a kind of general statement, but I think it's reasonably valid. They often, so the class 2 methanol masers, and I'm not going to go into too much into that, they get their initial pumping photon energy from radiation. So they need to be near sources of radiation. They also are going to have some, you remember this kind of the parameter space where water masers are produced. The methanol masers are also going to have some particular parameter space of density, temperature, stuff like this, where they can produce the maser emission. If it's too hot, they get thermalized. If it's not hot enough, then there's not enough radiation to produce the masers. So it just happens that the class 2 methanol masers, their ideal physical, like the conditions for producing methanol masers is the conditions you find in protostellar disks. Especially in the case of 6.7 gigahertz methanol masers, which I keep talking about because they're very popular actually. They tend to, pretty much always be found around high mass protostars. So yeah, each maser transition is going to have some kind of preference to a particular environment because of the range of physical conditions it needs to produce the maser emission. So in the case of SIO masers, these are also excited by radiation, so radiatively excited instead of collisions. And these are typically found in the shells of evolved stars. So as a star approaches its death, it starts to have these mass loss ejections where it produces these shells of material around the star. And in those layers, you typically get the necessary temperature, density, stuff like this, for the SIO masers to be produced. You very rarely see SIO masers in protostars. So, you can already see, like from this kind of plot, if I point my telescope at the sky and I find a 6.7 gigahertz methanol maser, I can say, okay, that object is a protostar. But if I point in another direction and I find a SIO maser, I can say, okay, in that direction there's a evolved star. So you can already start to see the uses of masers. So I want to warn you guys, because maser observations can be very dangerous. In terms of the interpretation, the way that you might interpret the data that you get. So, wait, I haven't been talking for 5 hours, am I? No, okay, good. Yeah, I want you to imagine the case of a masers in an evolved star shell. So I talked about this, maser, stars, as they're dying, they produce these mass loss ejections, and they produce these like layers, spherical layers around the star. So let's say we take this thing and we cut it, and this is what's shown now in the slides here. You have this spherical shell. So it's hollow on the inside, empty on the outside, and it's just got this shell. And you got some seed photons coming in, and they're gonna, interact with the masers, the cloud molecules in this spherical shell. Let's mention now, right, that all of these molecules represented by these little dots, they're in a cloud of gas, and that gas is in population inversion. So when a photon comes in, it's going to produce more photons and amplify exponentially with the path length, as you all know. So what happens, you got all these photons coming in, but in particular paths through this shell, there's going to be a longer path length. Let's assume that the observer is down here on the bottom right of the screen, right? So as the photons come in, if they take this big long blue path here at the top or at the bottom, there's going to be lots of instances of de-excitation. So there's going to be a lot of instances of amplification or stimulated emission, right? There's going to be a lot of instances of stimulated emission. So you end up with, 1 maser photon, 2 maser photons, 4 maser photons, 8 maser photons, and going up like that. So yeah, these long paths through the 3D shell are going to be really bright. But this path through the middle of the shell, through the center of the shell, so if you're looking at the thing like this, is this bit in the center, that's going to be really not very much path length between the behind the shell and yourself. There's not going to be very many instances of stimulated emission. So that region is going to be really weak, right? Whereas the region around it is going to be really bright. So what you end up with is a circular image. So this is the tricky thing with masers, okay? Because you got this 3D spherical shell, but what you see is a circle. You might initially look at the circle and think, oh, I've got a ring around the star. And it's like, no, you've got a spherical shell, but you have to take into account the fact that you have maser brightness is going to be proportional to the exponential of the path length. So you got to be careful with stuff like that. So then another kind of context for star formation, and I already alluded to this a little bit earlier, is the high mass protostars. So the disk of a high mass protostar has the right physical conditions, which is warm infrared radiation in disks. So that's where you typically find those. And then the water maser emission, as we've now mentioned enough times that I'm definitely sure you're going to remember it, they are produced in the shocks by collisions. So what you end up with is this kind of scenario here. And I just wanted to show basically just to convince you, because maybe you think I'm lying or making it up. Here's an example, observational example, where we saw this exact kind of case. So these circles with arrows coming off them, these represent the water masers that are in a jet, and that jet is being launched from a disk, which is represented by these triangles here. And the triangles are the methanol masers that live in the disk, and the circles with arrows are the water masers that live in the jets. So the important thing to mention here, actually, and this is one of the reasons why masers are so useful, is that we can't see that jet and we can't see that disk because we don't really have the observational facilities that can easily resolve those regions and even see them, because this whole system is happening deeply embedded inside a dense cloud of gas and dust. So the masers work as kind of observational markers for disks and jets, of disks and jets that we can't even see. So this is one reason why they're super useful. They're really bright as well, I should mention, masers. So we mentioned about the pumping conditions before. So assuming we don't pump the maser too hard and thermalize the molecules, if the shocks were to get stronger, the water masers would get brighter, right? So if we make the pumping conditions more suitable, you get more masers. And similarly, if the infrared radiation enhances, then the methanol maser is going to get brighter. So I think you can see where I'm going with this. Well, I guess I'll be coming back to that in a second. So the first conclusion that I want to discuss here is that the maser detections are strongly biased to the regions that have a long path length along the observer's line of sight. So yeah, what you're essentially seeing is a cross-section of your target. So if you were to have a sphere, what you'll see is a ring, this kind of thing. And the other conclusion, which is kind of a kind of mini conclusion for the entire talk so far, is that the amplification is sensitive to this path length, so how long the maser is in your direction, the radiation or collision, so the pumping, and so this is going to lead us to maser variability. So if your maser is getting longer or shorter, which doesn't happen often, but it could, or if the radiation field, so in the case of the methanol masers, if the disk is getting warmer, we might get brighter methanol masers, and if the shocks are getting stronger or weaker, we might get stronger or weaker water masers. So this opens the field of maser variability. And there's kind of a few different types of variability that we see in masers. So these two plots here, so I'll start with the top left one. The data points are the brightness of masers and where X is the time domain. So this is from a radio astronomy in Poland. They were monitoring the water maser and methanol maser emission over a long period of time. So basically, like on the x-axis, each of these is like, say, a different day of observation, and they monitored the brightness of the maser. The red line is the methanol maser. So you can see, like, on certain days, the methanol maser got really bright and then died down again, and then it was kind of relaxed for a while, and then it picked up again and died down again. And the water maser was doing something similar, but they were kind of anti-correlated. So when the methanol maser was bright, the water maser was weak. And this was a super interesting finding, because it implied that the energy in that region, in this case it was a star-forming region, was increasing and decreasing. And what was happening was I think, if I remember correctly, as the region got hotter, this was good for the methanol masers, so you produced more methanol masers because there was more radiation, warm dust radiation, which they like. So the methanol masers were happy, but the heat was too much for the water masers, which then thermalized the gas and dropped the flux of the water masers. So you end up with this kind of seesawing between the two, where the same physical conditions is happening for both masers, but one of the masers likes it and the other one doesn't, and so they kind of anti-correlate like that. So yeah, this is one super interesting example of maser variability. Then more kind of also very common ones, because periodic masers are quite uncommon, but non-variable masers are very rare. Like completely stable masers are rare. All masers will vary to some degree, but some of them are relatively very stable, so like they don't really change very much. Some of them are crazy, like some of them will get tens of thousands of times brighter in a space of a few hours and then go back down to nothing and pretend it didn't happen. And then some of them, so sorry, I'm digressing. Some of them will like gradually brighten. So if you look at this plot here, this is a spectrum. So this is a dynamic spectrum. So the x-axis is time, and then the the z-axis or y-axis is velocity. So each line along at a particular time is a spectrum. And let's say you take the emission that's happening at about 12 kilometers a second, you can see that it gradually gets brighter. Yeah, that's cool. Then you have some masers can gradually get dimmer. So if, for example, let's take the the water maser at like 2 kilometers a second, that's gradually getting dimmer. Then you have things called bursts, and this is where the maser just suddenly gets brighter and then typically will drop back down, either quickly or slowly. And you can see a burst happened at day 100-ish, and at about 3 kilometers a second. Okay, so you can see that there's various kinds of maser brightness, both for the water masers, for the methanol masers, same for the SiO masers. So I want you to, again, to take a little bit of time and discuss basically like 3 things, each with 2 points. So what is the energy source? So we talked about the maser pumping. What is the pumping energy source for water masers? And where are water masers often found? So what environments are they typically found? Then what is the pumping energy source for the methanol masers we talked about so far? And where are they typically found? And then what is the pumping energy source for the SiO masers, and where are SiO masers typically found? So yeah, have a minute or so to discuss this with your partners, and yeah, the assistants will be there to help you if you want to kind of check your ideas with them. Okay, so if someone can pause the video and then unpause it after a minute or so. And I'm gonna have a drink of tea. Okay, so I'm guessing you've unpaused the video now. So we talked about this maser variability, and the topic, I think this is possibly the last topic now that I want to mention then. Oh no, this is VLBI after this. Is maser monitoring. So this is the observational approach of monitoring the fluxes of maser emissions. So just seeing how the brightness changes over time. So this is something that's pretty straightforward, right? You have your astronomical object, it's producing masers, you point your telescope at the astronomical object, measure the brightness of the masers, and then do that every day for a couple of years. And then look for these events that happen in time where you have flares or periodicity or increasing brightness or decreasing brightness and stuff like this. So I'm just going to read this out because it's very long. So we already learned that the maser brightness can depend on path length, pumping conditions, and input seed photons. Therefore, by monitoring the brightness of masers using radio telescope, we can interpret any changes in the maser brightness as physical changes in the maser region. For this reason, there are many radio telescopes monitoring many astrophysical maser sources, and some examples of what they have found are newly launched protostellar jets. So this is the water masers, right? If you got some jets, this is going to produce collisions, that's going to produce the water masers. So pulsating evolved star shells. So we talked about the shells, like pulsating ones. So you know, if I were to quiz you, which I can't because this is recorded, but I would say, which maser transition is this? You'd all tell me it's the SiO masers, and I would give points to everyone. Then you have brightening of infrared sources due to protostellar accretion. So what was seen in this case was there was a high mass protostar with a disk and a jet, and the 6.7 gigahertz methanol maser got brighter, and so it was understood that this was happening because the star was getting brighter, or the region near the star was getting brighter, because it was accreting material from the disk. So these were all different astronomical events that were discovered because of the masers which were being monitored, showing some signs of variability or bursts or something like that. So those are some examples. Yeah. So, well, I can't stand there and ask you these things because I'm not there. But jets, collisions. This is the water mazes, right? Evolved stars, SIO. Then infrared in high mass protostars as the energy source. We all know now this is the methanol mazes. Okay, so we haven't yet talked about what a maser actually looks like. Okay, we've talked about how bright it is, what changes how bright it is, some like one equation, but we haven't talked about what they actually look like and how to even image them in the first place. So the two main ways of imaging masers. I should emphasize that we're talking about the masers that are at radio and submillimeter frequencies, right? Oh, I've paused. Hold on, everyone. Ah. Okay, hopefully the recording is still going and you can still see this. Yeah, okay. So we're talking about 1 second. Yeah, we're talking about radio and submillimeter masers. So there's also masers at, well, masers at optical frequencies are called lasers. So they're not masers, but you get what I'm saying. So I'm going to be talking about the radio. So the two kind of approaches that you can really take is the lower angular resolution observations and the higher angular resolution observations, and these are represented by telescopes like the Very Large Array. So this is the one from the movie Contact, ALMA, which is the Atacama Large Millimeter Array or something, but it's the absolute best, millimeter array that humans have made so far. And you have the Australian, the ATCA, Australian something compact array. Apparently you don't need to know these acronyms all by heart. We all know it as the VLA, ALMA, and ATCA anyway. So these are interferometers, and you're going to be doing classes on interferometers at some point, where the baselines are 1 to a couple hundred kilometers in length. And I'm going to resist talking too much about interferometry. It's one of my favorite topics, and I'll be here all day, so I'm not going to talk about it. But this gives you a resolution of tens to hundreds of milliarc seconds. Then you also have the VLBI, which is very long baseline interferometry. This is baselines of hundreds of kilometers per second, kilometers distance, and this gives you a resolution of milliarc seconds. So this image here on the bottom right is the VERA telescope. So there are 4 VERA dishes across Japan, and they produce a VLBI array that has the angular resolution equivalent to a dish the size of Japan or so. So typically, and this is not a hard rule, but radio maser astronomers will typically be in one or the other of these categories. And then you also have the single dish monitoring that we mentioned before, the maser monitoring. All of these are very complementary to each other. There are some people who do 2 of those 3 or all 3 of them. I myself mostly am VLBI. I think I've never touched the VLA or ALMA or ATCA like personally, and I don't monitor masers myself. So I'm a VLBI person. But yeah, they're all very much helpful to have, all of them if you can. I need to click these. So the kind of data that you get then, So the single dish radio telescope, so this is the monitoring stations that we mentioned before. They're just going to give you a spectrum. So that's what you see here on the left. It tells you how bright is the maser at each frequency. And if you have masers that's coming towards you, they're going to be blue shifted, and if they're going away from you, they're going to be red shifted. So you can kind of imagine here from this spectrum on the left, there's some emission, some maser clouds that are coming towards you and some that are going away from you, because you have this big difference in the velocity here. You have some very blue shifted and some red shifted masers. So these kind of observations, while they're not very highly detailed, there's some good information in there, and they're pretty easy to do. Right? It's pretty easy to point a single radio telescope at the sky and measure the radio brightness. And you'll be doing that yourself, so you'll see what I mean. Then the imaging observations, so from the last slide, this VLBI and VLA, this is much harder to do as a technique, but you do get a lot more information. So with this, you don't just get the flux and frequency, which you get from the spectrum, but you also additionally get the sky plane distribution. So you can literally now start to say, where is this emission coming from on the sky? So we talked about methanol masers being in disks, for example. We want to see that disk if we want to study disks. So we want to image those masers. It's not good enough just to have a spectrum in certain cases. So as you can see, so this figure here on the right, this is a kind of typical image of some water masers, and you can see that some are brighter than others. They're mostly round, some are a little bit extended. Each of them has like a slightly different velocity. They can overlap each other. This one labeled B here, this one actually was two masers that passed each other like that, and then the masers, the seed photons were amplified by the masers, which then came towards the observer, which then entered another maser, and then it got double amplified. So it was really cool. We were watching this and it just went boom. It just got super bright. So similar to the VLA, VLBA, like they both trace different different sizes of masers, but they're both very helpful to have. And in the case of single dish monitoring, it's good to have this time series, which the maser monitoring, which you can't do with the VLBI, and with VLBI it's good to have the imaging, which you can't get from the single dish. So complementary science. So then, one of the last things I want to mention is proper motions. So let's say we have, we now know what masers look like. Let's say we look at some masers, they look like this. There's just two masers in the sky, minding their own business. And then we leave it for a month, go and build a house or something. And then we come back and we observe again with the VLBI array, and we see the masers move now to here. And then we leave it another month, observe again, and leave it another month and observe again. So we can see that this maser is moving across the sky. And one of the masers is moving fast and the other maser is moving slow. So this is one of the very big advantages of using masers. Because they're so small, you can actually see them move. So you notice how like when you look at a bird fly across the sky, it looks like it's going really fast. But when you see an airplane go across the sky, it looks like it's going really slow. Of course, the airplane is going much faster than the bird. It's going hundreds of miles an hour. But the bird is small. So compared to its size, it can pass its body size in a very short amount of time. Whereas a plane takes a long time to pass its body size. It makes it look like it's moving slowly. The smaller you are, the easier it is to see motion, is what I'm trying to get at. So because masers are very small, they're like milliarc second size. If they move by a milliarc second, you can see that. Whereas if you have like a cloud that's at one degree in size and it moves by a milliarc second, you're not going to see that, right? You're not going to be able to detect that motion. So because masers are small, we can look at these proper motions. And this is kind of highlighted in this figure that I'm bringing back from earlier, which shows the jets. So these circles with lines, arrows coming out of them, these are the water masers in the jets. So we actually observed these masers for several months, and we could see that they were firing out like that. So this is something that you can only really do with masers. And I don't know how much longer this will be, but at least in cases of star formation, this is only something that you can really do with VLBI. Or, these are dangerous statements, so I would just say then, this is something you can do with VLBI, and most people do this with VLBI. It's probably the safer statement. So yeah, because they're small, you can get proper motions. So, because they're small and you can get proper motions, you can also make movies with them. So what you're looking at here, we mentioned the AGB, so evolved stars, and you have these SIO masers in the evolved stars, in these shells, and because, bringing everything together now, because masers amplify by path length, this shell is going to look like a ring, which you can kind of see already here. And because the masers are small, if they move, we'll see them move. So we mentioned before these pulsating shells. That's what we're going to be looking at here. Okay, you ready? Look at that. So you can see, bearing in mind everything we've learned now, the SIO masers are pumped by radiation. So what you're seeing here is the regions where the energy conditions and density conditions, temperature conditions are just right for the masers to be produced in those regions. So it might not be that you're actually seeing physical motion of gas. It might be that the gas is not moving, but the region where the energy levels are right, so the region where the temperature is right and stuff, maybe that is moving through the gas which is not moving. Potentially, it's hard to tell, right? But anyway, these are the kind of beautiful things you can do with masers. This region is very small, right? This is going to be a couple of 100 milliarcsecond size or so, much smaller than a degree. But you can make these images. This would have been made with the VLBA, the American VLBI array. So yeah, that's the pulsating shells in a evolved star. And I'm just going to run it a few more times because I think it's really cool. Keep your eye up here. There's like a thing that seems to fall inwards. That's really cool, right? So yeah, I really like these kind of movies. And then another example, so we have Orion Source I, which is a high mass protostar. And it has a disk which is represented by these white contours, and it has a rotating outflow which is measured in molecular lines, which is showed in color here. So I just wanted to give you a little bit of context. What happened then, if you zoom in on this disk region in the center and image I think this is one of the rare cases of SIO masers in a high mass protostar. But if you make a movie with this, so you can imagine this black lane here is where the disk of dust, and then you have these outflows coming off to the top left and bottom right, and the water masers are in the shocks. Sorry, I can't remember if these are water masers or SIO masers. It doesn't really matter, but they're in like the edge of the outflow cavity here. And so again, this is multi-epoch VLBI observations to make a movie. So here we go. Bam. That's so cool, right? You can kind of see a sense of rotation, right? And an ejection from the start. So these are the extreme cases of proper motion investigations with masers. And that basically brings me to the end of the lecture. It got pretty long. I can't take questions, which is very unfortunate because I'm not there. But if you have any questions, well, if possible, I might be able to join by video link during the day when this lecture is actually given. If not, then I'm sure someone at hand will be able to answer your questions. And in the last case, you can always just send me an email or something as well. Anyway, I'd like to thank everyone for your attention, and yeah, Hope you enjoyed learning about mesas. I think they're super cool. You can probably tell by how excited I got by the movies. But yeah, you'll be doing some stuff on mesas using the dish in a few days or so. So yeah, thanks very much, and I'll see you next at the polarization lecture. Bye.